Good morning students, welcome back to online classes of analog communication. In last class we have discussed about your pulse width modulation technique. I hope you all remember what was a pulse width modulation technique. Some of the students are writing notes, they are submitting the assignments, that's very good. Okay, and the remaining some of the students, I hope they are looking to the videos, they are also making the notes. Most of the students are coming up with the doubts. So it's my request to everyone to please to watch the videos and do practice the equations and problems, right? So we'll just revise what we have discussed in the last class. It was about your pulse width modulation. What is this pulse width modulation? These all techniques are about one analog pulse modulation schemes. Yes ma, I hope you all remember what are analog pulse modulation schemes. We have seen pulse amplitude modulation, right? Then we have seen the pulse time modulation techniques. In pulse time modulation we are having two types, that is pulse width modulation as well as your pulse position modulation. In today's class we are going to see about your pulse position modulation technique. Okay, so before going to pulse position modulation, we'll just quickly revise what was your pulse width modulation. So what was your pulse width modulation? What was the definition? Okay, what you are seeing there, the modulation technique in which the pulse width is changed or varied in accordance with the instantaneous value of your message signal. Isn't it or not? So the width of your pulses, that is your carrier, you are having the pulses over there. So the width of the pulses is changed or varied in accordance with the instantaneous values of your message signals are called as your pulse width modulation. So we have seen there will be having three different techniques, right? So we are having leading edge modulation, then we have seen trailing edge and center edge. So pulse width modulation is mostly done in which technique? Leading edge modulation technique, right? But in pulse position, you remember we always consider trailing edge. Just for a note, you remember this one. Okay, so what were the advantages there? And what is the how we are going to generate this pulse width modulation? Simply, very simple method to take a comparator, right? To that you are having two inputs. You give input for message signal as one input and sawtooth generator or the sawtooth signal generator as another input. You will be getting a pulse width modulated wave. Okay, then after for the demodulator side, what you are going to use? You are using a ramp generator, then a reference pulse generator, then you are having a low pass filter, then you are using a clipper to clip off all the noises which will be occurring when you are transmitting the signal from transmitter to the receiver through a particular channel. So compulsory there some noise will be added when you are transmitting your message or the data from transmitter to the receiver through a particular channel. Okay, so that was your pulse width modulation, and noise was very less comparatively with the amplitude modulation. In which one? Pulse width modulation. Signal to noise ratio is also good. Signal and noise separation was also very easy in that one. Okay, and synchronization was not important in that one. But what the disadvantage was, we are having larger bandwidth. Of course you require a larger bandwidth, and the pulses which are varying in width, therefore they require the power which we require is high, and the power will also be varying. So that were the two disadvantages. So as to overcome that one, we are going for next modulation technique, that is your pulse position modulation. I hope by name itself you remember what is meant by pulse position modulation technique. So what it means by pulse position modulation? You are varying the position of the pulses in accordance with the message signal, right? So in general, first I am telling what is a pulse position modulation. What actually we do, the position of the pulses will be varying in accordance with the instantaneous values of your message signal. Okay, so we'll see in what we are doing in the pulse position modulation in today's class. Okay, we'll get started up with that one. So in pulse position modulation, the information is transmitted with the varying position of the pulses. I am giving the introduction for this one. So what we are having, the information is transmitted in the varying position of the pulses. How we are going to transmit your information? Whenever your position of your pulses, because in pulse position modulation we are your amplitude as well as the width should be constant and your position should be varying. So your whole data or the message or the information is transmitted with the varying pulses of your varying position of your pulses. Clear? So the basic idea about the generation of ppm waveform is that here, as amplitude of the message signal increases, amplitude means the waveform, your sinusoidal waveform of your message signal. If it is increases, the pulse shifted according to the reference. Okay, this is how you will be moving. What I have said in the definition, the position of the pulses will be varying in accordance with the instantaneous values of your message signal. So whenever the amplitude of your message signal is high, the position will be changing. Position of your pulse train will be changing. Similarly, when it is low also, it will be changing depending upon the instantaneous values of your message signal. Okay, the width of these pulses will be remain constant and only the position will be varying. So the amplitude as well as your width will be constant for your pulse train, and what will be varying? Your position will be varying. So thus the power transmission does not show variation, but whereas in your pulse width modulation there is the power transmission. Whenever the amplitude of the message signal is varying, the width is also varying. That means your bandwidth is increased. That is one disadvantage. Larger bandwidth we require, and the power is also varying, so we require more power. So that are the two disadvantages that we have in your pulse width modulation technique. Now we will see the definition of your pulse position modulation. The technique that allows variation in the position of the pulses according to the amplitude of the sampled modulating signal is known as your pulse position modulation. This you can also define, or simply you can define as the position of the modulating signal can be varied in accordance with the instantaneous value of your message signal. Okay, both are well and good. So if you write this, it will be much more professional. Okay, so the modulation technique that allows the variation in the position of the pulses according to the amplitude of the sampled modulating signal, that is nothing but your message signal. So the variation of position of your pulses are varied with respect to your amplitude of your message signal, and that kind of modulation is known as pulse position modulation. I hope you are clear with the introduction of your pulse position modulation. Clear, ma? So we'll see now. You will be having a question. The question arises how the position of the pulses show the variation. Okay, how we are going to vary the position particularly. I have said just the position has to be varied, but how we are going to vary that particular pulses. Okay, so that is the question. So the pulse position modulation signal is generated in reference to the pulse width modulation signal. Okay, the very important thing for generation of your pulse position modulation is that first you have to generate the pulse width modulated wave, then that it has to be kept in reference, and you have to go for the pulse width modulation. Directly we cannot opt for pulse position modulation. You have to generate first the pulse width modulated wave, then that should be taken as the reference signal, then you have to go for the pulse position modulation, then positions that can be changed. Directly you cannot go for the pulse position. Okay, so how the question is how you are going to have the pulse position, how the positions will be changing. So what is the answer that you will be giving? The pulse position modulated signal is generated in reference to the pulse width modulation signal. So what I have said in the initial of the class, in the starting of the class, the trailing edge of the pulse width modulated signal acts as the beginning point of the pulses of the ppm signal. See, I have clearly told you in the last class what are the trailing edges, what are the leading edges. Okay, mostly pulse width modulation we consider the leading edges modulation, right? So trailing edges can also be considered, but in pulse position modulation we always consider the trailing edge of the pulse width modulation. The trailing part we have to consider that is taken as the reference signal, and the trailing edge of pulse width modulation is the beginning point of your pulse position modulation. Okay, I hope you will remember. I'll show the figures also, so that will be clear for you people. Okay, now the transmitter has to send the synchronizing pulses or simply the sync pulses to keep the transmitter and receiver in the synchronization. Okay, these sync pulses helps us to maintain the position of the pulses, and in this pulse position modulation it is very important that the pulses which are used in the transmitter as well as the receiver side, they both should be synchronized. The both should be in synchronization. Okay, this is very important in your pulse position modulation. So the transmitter has to send the synchronizing pulses to keep transmitter and receiver in synchronization. So they both have to be synchronized. These sync pulses help us to maintain the position. If they are not synchronized, the positions will be changed. If the positions are changed, you may lose the data and you may not be get the proper data at the receiver side. So synchronization is very important in your pulse position modulation. So these two are the queries that we will be having in your pulse position modulation, right ma'am? So how we are getting this pulse position modulation? First you have to go for preparing the pulse width modulation signal, that will be the reference signal, and the trailing edge of the pulse width modulated signal will be the beginning point of your PPM signal. Okay, and the transmitter and the receiver, they both should be synchronous. The pulses which are used in or which are transmitter at the receiver, they both should be synchronized to maintain the positions of the pulses. Clear? Now we'll see the generation of your pulse position modulation techniques. As I've already said, we need a pulse width modulated generator first. We have said that for reference we need pulse width modulation signal. So first what we have to do, we have to generate a pulse width modulated wave. The whole generator what we have used in pulse width modulation. You remember we use a comparator, a modulating signal, a sawtooth generator, and that is given to a monostable multi-vibrator. Why we are using monostable multi-vibrator? Because it is negative edge triggered. Yes, I hope you remember. So in DE I think you have remembered about this. You have learned. So in negative, these monostable multi-vibrators are negative edge triggered. We require trailing edge triggering, right? So that's the reason we are using this monostable multi-vibrator. So it is very simple to design that pulse position modulation. How we are going to design? You just take a pulse width modulator generator. To that you have to add simply a monostable multi-vibrator. Then you will be getting a pulse position modulating signal. Okay, this is the PAM signal, or direct message signal can also be applied over here. Then you are using a sawtooth generator. Here you will be generating a pulse width modulated signal. This reference signal or the pulse width modulated signal is given to the monostable multi-vibrator, which takes out your pulse position modulating signal. I hope you are clear. Okay, the output of the comparator is fed to the monostable multi-vibrator as it is a negative edge triggering. Hence, the trailing edge of the pulse width modulating signal, the output of the modulation signal goes high. Okay, whenever you are having the trailing edge of the pulse width modulation, what we have said, at the trailing edge of the pulse width modulation, it will be the beginning point for the pulse position modulation. So whenever you are having the trailing edge of the pulse width modulation, then your monostable vibrator gives you a higher answer. So the output of the monostable multi-vibrator goes high, means your PPM will be going high. This is why the pulse of the PPM signal starts there and within the trailing edge. Correct ma? I hope you are clear. I'll repeat it once again. Whenever you are having the trailing edge of your pulse width modulation here, then it is given to the monostable multi-vibrator. When it is having trailing edge, your PPM signal will becomes high. This is why the pulses of the PPM signal begins with the trailing edges. Okay. Now we'll see the figure. See what you are having over here. The generation of pulse position modulation. You are having this, you are having the message signal, and this is the carrier signal, right? These both are in combined. You will be having a pulse amplitude also and pulse width also. This is the pulse width modulator signal. The amplitude of your message signal is high, the width is also high. Right? And which is this, which kind of what we'll say method, pulse width modulation? This is leading edge. See, my edge is same, leading edge is constant. Okay, we will see the leading edges only. So leading edges will be constant. So this is the pulse width modulation. Whenever the maximum message signal is there, you will be getting the width will be increased. When you are having the lowest voltage or the lowest amplitude value, then your width will be decreased. Now this up to here you got the output over here, correct, after the comparator. This is the pulse width modulator signal. Now this is fed to the monostable multivibrator, which gives a negative edge triggering. So what happens, as we have said initially, whenever you are having the trailing edge of the pulse width modulation, this is low, then obviously it becomes high. Yes, you remember here, as I have said, the trailing edge of the pulse width modulating signal acts as the beginning point of the pulses of your ppm signal. This is the trailing edge. I am repeating again and again. See here, at the trailing edge of the pulse width modulated signal, you will be having the beginning of your which signal? Pulse position modulated signal. So I got a signal over here. When you are having the peak, your value has been increased, my position again I have changed. It completely depends upon this reference signal. So whenever you are going to generate a pulse position modulated signal, you have to have a pulse width modulated signal as a reference. When this signal is there, then obviously see here at the trailing edge your position is changed. Now see at this trailing edge again your position. The maximum voltage of your message signal is your position is maximally moved from this point to this point. This much gap is there. Again if the voltage is decreasing, the position width also decreasing, and the position has been moved. Again the position has been. The trailing edge of the pulse width modulator gives the initial beginning of your pulse position modulation. So this is how the position of the signals is varied in accordance with the message signal. So whenever you want to change the positions, you have to go for the pulse width modulation and then you have to go for the pulse position modulation. So generation of your pulse position modulation is completely same as of your PW generator. You need a PW generator. To that PW generator you have to add a monostable multivibrator because it is a negative edge triggered circuit. So that's the reason we are going for that one. I hope you are clear with the generation of your pulse position modulation signal. Okay, now see, we are seeing the detection or the demodulation of your pulse position modulation. For generating of your original message signal, you have to go for this one. Okay, so what you are having in this one, you will be having a pulse generator. As we already said, there should be synchronization between your transmitter as well as the receiver. So that's the reason we are using this. So the detection of the pulse position modulation consists of a pulse generator and a reference pulse generator. They both are fed to a SR flip-flops. Okay, then that is given to the PWM demodulator, from where you will be getting your original message signal. Okay, now we are first what we are doing, we are converting your pulse width modulated signal. First pulse position modulated signal is there. To that we have to convert that signal into pulse width modulated signal, correct or not? From pulse width modulated signal, the same go back to your pulse width modulating signal. What you are having there, you have to use what you are having, clippers, then you are having a low pass filter, then your original message signal. This whole pulse width modulator consists of all that. So just first what you have to do, you have to convert your pulse position modulated signal into pulse width modulated signal, and that pulse width demodulator, what it does, it converts back your modulated signal into the message signal. Correct? What you had in your pulse width demodulation side, you remember you are having a ramp generator and a reference pulse generator, then you had a clipper, then you are having a low pass filter. I'll give the link of the previous class also, just refer that one for the demodulation side. Okay, so if directly you will get message signal, but thing is first you have to convert the PPM signal into the PWM signal. So the demodulation circuit consists of a pulse generator, a reference pulse generator, an SR flip-flop, okay, and pulse width demodulator circuit. These four components are very important for detection of your pulse position demodulators. Okay, now see, the pulse position signal transmitted from the modulation circuit gets distorted by the noise during the transmission. This is must and should, isn't it or not? Whenever you are modulating, modulation is nothing but combination of your carrier and message signal. These both are combined and they are transmitted through a particular channel. Some kind of noise or distortion will be compulsorily added to your modulated signal. Okay, so here also we are seeing the same thing. The ppm signal transmitted from the modulation circuit or the transmitter will get distorted by the noise during the transmission, and this distorted ppm signal reaches the demodulator circuit or your receiver. Yes, correct? So this distorted ppm signal reaches the demodulator circuit, and the pulse generator employed in the circuit generates a pulsed waveform. This waveform is a fixed duration which is fed to the reset pin of your SR flip-flop or the R flip-flop. So what you are doing here, we are generating a pulse. You are using a pulse generator which produces the pulses which is having the fixed duration. It won't be changing because we need a fixed duration. If it is changing, the position will be changed. If positions are changed, then you may not get the proper data. So what you are doing, this pulse generator gets the fixed position pulses, and that is given to the reset pin of your SR flip-flop. Now this reference pulse generator generates a reference pulse of a fixed period. It is fixed position you are having. Yes, we are having fixed duration over here, width is constant, and you are generating a reference generator generates a reference pulse of fixed period which a transmitter, when transmitted ppm signal is applied to it. Okay, here this reference pulse is used to set part of your flip-flop. Okay, and this set and reset signals will be generating your PWM signal, that is nothing but your pulse width modulated signal at the output of the flip-flop, and this output of the flip-flop is fed to the pulse width demodulator circuit. I know what's the operation which is going on at your pulse width modulation. I hope you remember, ma. This last point has been missed. I'll repeat it once again. Do write it down. Okay. This what in the first reset part, what you are applying, a pulse generator output is given to the reset button. What you are having in the pulse generator output, the output what you are getting there, we are getting a pulse trains if we which are fed to the reset pin whose duration is fixed, right? Here at the reset pin you are getting the pulses whose duration is fixed. At the set pin we are getting a pulses whose periods is fixed. Means here time you are fixing, their width you are fixing. So due to this one, what you will be getting the output of your SR flip-flop, you will be getting a pulse width demodulated pulse width signal or the pulse width modulated signal. Pulse width modulated signal means the widths will be changing. So what you have to, that is given to the pulse width demodulator circuit. In pulse width demodulator circuit, you will be having a ramp generator and you will be having a reference pulse generator. Then it is given to your clipper where you will be clipping off all the external voltages, because we are having some reference voltage in your what we will say clipper. Okay, it only takes the sum of the voltages which are required below the threshold. It will be removing all that one, and that clipped signal is again given to your low pass filter, which smoothens your original message signal and gives the output. Okay, so this last point is about this set and reset pins or the reset signals generate the pulse width modulated signal at the output of the flip-flop. This output is fed to the pulse width modulator circuit, pulse width demodulator circuit, which in turns produces your original message signal. This is how you will be generating your original message signal from your pulse position modulation technique. I hope you are clear with the pulse position modulation technique, correct? So this was about detection or the demodulation of your pulse position modulation. Now if you see the advantages and disadvantages of your pulse position modulation, what you are having, It is similar to the your pulse width modulation. In ppm, amplitude is constant and thus less noise interference will be occurred. Yes or no? You will be having of course less noise because your amplitude is not changing. If amplitude changes, you will be getting more noise. Okay, we go back to the sampling, flat top sampling, natural sampling. You just see that one, you will get to know how noise is getting affected, right? So similar to the pulse width modulation, pulse position modulation also shows better noise immunity as compared to the PAM because the amplitude is constant and thus it is having less noise interference. So what it is? This is so because information content is present in the position. Okay, we are varying the position, not the amplitude of the pulses rather than the amplitude. Why we are saying that it is having better noise immunity when compared to the PAM? It is because the information content is present in the position of the pulses rather than that of your amplitude. As the amplitude and the width of the pulses remain constant, the transmission power also remains constant and does not show variations. This was the disadvantage in your pulse width modulation because the widths they are varying, your power is also varying. That was a disadvantage. Yes or no? So here the amplitude is constant, noise immunity has been increased, and your width is also constant, so your power transmission is also constant. So these are the two advantages of this one, correct? These were the two drawbacks of your pulse amplitude and pulse width modulation, which are completely overcome in your third technique, pulse position modulation. Yes or no, ma? So the transmission power also remains constant and does not show any variations. Now recovering a ppm signal from the distorted ppm signal is quite easy because we are having a reference pulse width modulated signal. And interference due to noise is more minimal than that of your PAM and PWM because width is not varying and amplitude is also not varying. So occurring of interference is very minimum in this one. But you are having two disadvantages also. The thing is, as I have already said, there should be compulsory synchronization between your transmitter and receiver. That may be sometimes a disadvantage. Yes or right? Yes or no? So in order to have the proper detection of the signal at the receiver, the transmitter and the receiver must be in synchronization or synchronous. Yes or no? So this is the disadvantage. If you are detecting the signal at a receiver similar to the transmitter, that is well and good, easily you can detect your message. In case if you are not having synchronization, that is a drawback of your pulse position modulation. One is that, and second is of course the position bandwidth requirement is large. Because you are changing the positions, of course you require the larger bandwidth. So these are the two disadvantages we are going for the pulse position modulation. When it comes to your applications, this technique is mainly used in optical communication. Okay, you have seen the optical wires, CT cable wires, they are all your optical communication wires. So this technique is mainly used in optical communication systems and in radio control rooms or radio systems and also in military applications. This also used mostly in smart cards. Okay, contactless smart cards, high frequency RFID cards, tags, etc. So these are the applications where you will be using your pulse position modulation technique. I hope you are clear with today's class. What is about your pulse position modulation technique? Okay, how you are going to generate that one, how you are going to detect that at the receiver side, what are the advantages and what are the disadvantages that you have seen, and what are the applications, right? I'll just revise it once again. What is pulse position modulation? Position of the pulses are varied in accordance with the instantaneous values of your message signal. As to generate, for the generation, what is important? You require a pulse width modulated wave. So the generation of your ppm requires a PWM generator and a monostable multivibrator. Why we are going for the monostable multivibrator? Because the starting or the initial point of your ppm starts with the trailing edge of your PWM signal. So you require a PWM signal as a reference signal through which your beginning point of the pulses of pulse position modulation signals will be starting. And synchronization is very important for your pulses at the transmitter and the receiver side. At the demodulator side, what you are having? you require a pulse generator where where you will be getting the fixed duration pulses, and reference pulse generator which produces the pulses which are having the fixed period. These will be setting and resetting, which is given to the flip-flop. That flip-flop generates the PWM signal, that is pulse width modulated signal, and that pulse width modulated signal is given to the demodulator of your PWM. You know what is the operation in the PWM demodulator, and at last you will be getting the message signal. Okay, and these are the advantages. Your noise immunity is increased. Okay, width as amplitude and width both are constant, so the power transmission is also constant. It is very easy to get the message. Recovering the message signal is very easy in PPM, and it is very minimum noise is affected. But only disadvantage is bandwidth. Of course, the bandwidth we require is large because the positions will be changing. It requires a larger bandwidth. And one more important thing is, to detection of your signals, you require the synchronization between the transmitter as well as the receiver side. And the applications they will be using mostly in optical communication, radio communication, or itself in the military. I hope you are clear with today's class. We will stop the class here itself. Okay, in case of any doubts, please do let me know. Thank you.